My dad was supposed to fly out Clark the day before everything shut down.
Yeah.
And deep in some pretty interesting theory to show off.
It seems like ages ago, right?
Catching up.
Well, it's almost 5 years ago.
Exactly.
Should be nice.
Time flies.
Oh yes.
It's already been applied.
Okay, to be fair, chemists have
People seem to be making up about the lost interaction now. I get this notice of conference workshops every day.
We're back to normal, right?
Yeah, like, I don't know if it's normal.
We're back to abnormal.
It's abnormal. It's just like there's just so many of them. Right? Yeah.
Yep, sure.
Still having mixed feeling now because I agreed to go to the whatever last thing in May. Now just trying to make my plan yesterday. When I look at it, this whole thing is like a week-long thing, and then I would have to fly there myself and then pay whatever
1 week.
registration. I'm not gonna go there for 5 days.
I couldn't believe it.
No? Good to see you.
It was actually a quantum like it was impossible.
Yep.
It was interesting. I didn't see
our one and only Nobel laureate. We have 20 seconds for him.
Still going. I don't know. Yes, I'm sitting with the students.
Oh, maybe 20 seconds.
Come on, you didn't make me do something.
I don't know what it is. Maybe you forgot something. Yeah. All right, we'll get going. So it's my pleasure to welcome Dr. Alexander Petroff from Clark University. And Alex got his PhD training from MIT, listened to the geological physics, I think, and then something like that. And he was actually doing work related to astrobiology. And then he went to Rockefeller to do a postdoc in the Lipschitz group, who is probably one of the living, most known biophysicists. After a number of years of postgraduate training with all sort of fellowship, I cannot remember, just briefly looking at his CV. He did a year visiting position in the biology, on the biology faculty somewhere, I forgot, right?
Oh yeah, I did.
Right. Where was that?
That was at Bard College.
Yeah, Bard College. Okay. And then he started in the faculty position at Clark University. That's where he has been for the last number of years. He came to my attention through actually a student we admitted to our PhD program, Alexandra Rosselli Calderon. I don't know if some of you may know her. She was here briefly. She was supposed to do biological physics. I interviewed her, but after she came in, she wanted to do computational physics. And then one thing led to another. I think he was trying some, astrophysics, and then he transferred away. So I kind of lost track of her. But I, came to attention of Dr. Petroff's work. It's really interesting dealing with magnetotactic bacteria. So I visited Clark last year and I've been meaning to bring him on campus over the past year. So I'm glad you are here.
Thanks so much.
The stage is yours.
I've had a lovely time. Thanks so much to everybody, and let's get to it. So I work in a physics department. Sort of the questions I've been most interested in recently are trying to understand ecology, and the sort of difficulty with understanding ecology is that so much of what people do is they take bacteria from the natural world, bring them into the lab, domesticate them, and then study how these bacteria move about and interact with one another. And it's hard to go from that back into the real ecosystem. So what I'm going to try to do today is set up an ecology problem and then show how some sort of simple physical reasoning can help you understand bacteria in nature, hopefully a little bit better. So to set up the ecology problem, this is the system that I look at. So this is if you go to Cape Cod and you take a shovel, you stick it down into the mud, and you look at the top couple centimeters of mud, you see this interesting banded structure. And what's happening here is that top layer up at the top is in contact with the water. And so oxygen diffuses down from the surface water into the sand where it's consumed by the bacteria. So you get constant oxygen, and then it gets exponentially consumed. And after about a millimeter or so, there's no appreciable oxygen left. So you get this band up at the top where everybody's breathing oxygen. And then if you go down a little bit, everybody's doing something else. So there are these distinct strata where different bacteria and different strata are doing metabolically different things. And all of these strata are just reflecting sharp chemical gradients in the sediment. And so what makes this an interesting place is if you're living right here, if you go up a little bit, you burn to death because oxygen kills you. And if you go down a little bit, then you suffocate. So all of these bacteria need to position themselves vertically within these gradients. And to make life all the more difficult, these gradients move continuously. So when the sun comes out and the sun starts shining, photosynthesis at the top begins and you start producing a lot of oxygen up in the top millimeter. And now instead of oxygen going down 1 millimeter, it goes down 2 millimeters. So if you're a bacterium living in here, you're constantly needing to move up and down through the sediment. So all of this is to say that it's really useful to be able to tell the difference between up and down. So the way that we do this is that we sense the gravitational field. So, bacteria have been working on this problem for 4 billion years. So you've got 4 billion years, let's say that's a trillion generations, about a trillion bacteria on Earth, so not more, way more than that. You've got, 10 to some large number of bacteria, and they're all exponentially exploring they're all solving this problem in parallel to find all the different ways that you could possibly outcompete your neighbors. So in this time, in this massively parallel exploration of possible phenotypes, they found not only ways of telling the difference between up and down, but really every possible way of telling up from down. So there's the sort of obvious way of, you can measure gravity. You can put something heavy on one side of yourself, and that will turn you. There's some gravitational torque, and that's a good way to tell up from down. Turns out that gets difficult because as you get smaller and smaller, the gravitational torques get smaller and smaller, and at some point it's just too difficult. If really what you're interested in is sensing the chemical gradients, then just directly coupling your motion to the chemical gradient seems like a good idea, and there are plenty of bacteria that do that. Up at the top, you also have light gradients, since the sun is shining down on the surface, and so you can also tell the difference between up and down by saying it's bright up and it's dark down. So all of these different methods have different strengths and weaknesses, and so they all sort of coexist somewhere in the universe, somewhere on Earth at least, presumably in the universe as well. So these are the sort of obvious ones that you can do. You can also look for non-obvious ways of telling the difference between up and down. And so one of these is to couple your motion to the geomagnetic field. So if you take out a compass, I have no idea what direction north is here. I've got a terrible sense of direction. This way? Okay, cool. So if you have a compass, it'll point this direction, but that's a lie because you're only using a two-dimensional compass. In fact, north is more like this direction because we're at sufficiently high latitude that the field lines are curving back towards the center of the Earth. So if you swim due north, you're mostly swimming down. So regardless of which one of these fields you couple to, you've got this problem that you have to solve of you need to move either up or down, so you want to move along field lines, but you're also moving through this dense packing of grains. So you're constantly bumping into stuff all around you. So you're moving this highly confined geometry, and you're trying to find the narrow passageways between sand grains that will let you move vertically through the system. So what I'm interested in is how do you tune your phenotype to be able to balance obstacle avoidance with coupled to this external field. So we want to study these magnetotactic bacteria. So what you do is you drive out to Cape Cod, you find little muddy ponds like this, the whole thing stinks of sulfide, and you stomp around in here, and you fill up buckets full of mud, and you bring these buckets back to the lab. Right here I've stuck some magnets to the side of it, and if you wait for about 20 minutes, you go in with a pipette and you sample from the surface of it. And you find a very high concentration of bacteria that look like this. So these are bacteria that swam towards the surface of the magnet. I'll show you them responding to the magnetic field in a moment. But for the time being, let's just trust that these things swim in the direction of the magnetic field. Something that's really weird about this is that this is not actually a bacterium. This is 50 bacteria all tied together. So you can just see the edges of one bacterial cell here. So this is a spherical shell of bacteria. This is the world's only known obligately multicellular species of bacteria. So a lot of the work that we're interested in is trying to understand how physical interactions between organisms in these proto-multicellular conglomerates are able to get everybody to cooperate. As the bacteria within this little clump grow and divide, the whole thing swells up, elongates, and divides symmetrically. So this really is a multicellular bacteria. Super cool. In addition to being multicellular,
I assume they're motile?
they're very motile.
How do they move around? I mean, I'm just dying with anticipation.
So each individual bacterium has about 30 flagella on it.
Okay.
So one of these little spheres has 1,500 flagella. And so how all of those bacteria within that consortium are able to exert a force in a specific direction is unclear. Right? The way that these things do magnetotaxis is absolutely magnificent, and I have embarrassingly little to say about it. So what we're trying to do right now is do PIV around these things to be able to invert the flow field around one of these swimming bacteria for the distribution of forces on it. So we can just see like what fraction of the bacteria are actually pushing and pulling on the fluid. It turns out experimentally that's really hard to do. The most basic reason is, first of all, you have to get these from the real world. You have to start with a bucket full of mud. The other problem is if your magnetic field isn't horizontal to within a degree, and these things are swimming between a 40 micron gap in your microfluidic device, immediately everybody's just being dragged along either the bottom surface or the top surface. So actually visualizing the flow field around these is really difficult. I think we're going to be able to get it this summer, and then I'll be able to say more intelligently how it is that these things are able to actually swim together. But it's a magnificent question. So these things are multicellular. They grow and divide in this coordinated way. They're all pushing and pulling on the fluid together to exert a net force in a single direction. And everybody has a magnetic moment. So if you look at them in cross-section, you see these little black spots. There's our little crystals of magnetite. So each one of these crystals has a permanent magnetic moment. All of these magnetic moments line up within this consortium to point in a specific direction. And now, like, this is amazing, right? This is a group of bacteria that have broken two spherical symmetries. You get all of your magnetic moments to point in the same direction, so that the entire colony has a net magnetic moment. And you get everybody to rotate their flagella in such a way that they exert a force in a concerted direction. And so you exert a force that's parallel to your magnetic moment. How these bacteria are able to coordinate that is a magnificent question. And all I've got right now is speculation. I hope this summer I'll have some data about that. But for the time being, what I can do is tell you about how they actually move through the environment.
Can I ask another question?
Of course.
So how do they get those magnetite crystals?
They build them atom by atom out of dissolved iron in the fluid around them. They do that with such perfection that the quality of those magnets are similar to what you get in an industrial hard drive, except instead of building it in a clean room, you build it in
mud.
In that.
Cool.
But smaller.
But small. I mean, yeah, but yeah, a fair point. All right, so let's talk about how you actually do magnetotaxis. So the whole trick of magnetotaxis is that you have a permanent magnetic moment. So even if you kill the bacteria, if you turn the magnetic field, all the pile of corpses will turn with the magnetic field. There's no behavioral change that lets you do magnetotaxis. That part is purely passive. You just turn to align with the magnetic field. The trick is to exert a force that's parallel to it. So as you turn, you're also swimming in the direction of your magnetic moment. So you turn to a line like this, and then you swim along a magnetic field line. So let's watch that happen. So here's one of these So I'm going to say the word consortium a lot. A consortium is just one of these little groups of bacteria. So every little swimming thing that you want to call a bacterium, I need to say consortium, because it's actually 50 bacteria all tied together. So here's one consortium. Here's another down here. I'm going to start off with a magnetic field pointed straight upwards. And then about halfway through the video, I need to turn the field 90 degrees. And you're going to see a blue arrow. And the blue arrow shows you the average direction that everybody's swimming. And the mouse isn't working. There we go. So everybody's initially swimming more or less up. And now I turn the magnetic field. And the whole sort of flock turns to align with it. So this movie is slowed down by about a factor of 3. So these things quickly align with the magnetic field.
What's the magnetic field strength here?
Here it's about 4 times Earth's magnetic field.
Okay.
But they naturally turn in the geomagnetic field.
Cool.
So it's easy to build a mathematical model of this. You know, all you do is you say there's a magnetic torque acting on the bacteria. It's m times b, or the cross product of m and b. In 2 dimensions, you get m times b times sine theta, which is the angle between your magnetic moment and the ambient field. So there's a magnetic torque that's aligning it. And then that's balanced by a viscous torque, which is just slowing you down. So mu rot is called the rotational hydrodynamic mobility, and it's just the proportionality constant between the torque and the angular velocity. So if you solve this equation, you know, at least in the deterministic case, the black line here is the prediction rescaled by the alignment rate, and it works reasonably well, and you can measure the magnetic moments. If you look at the fluctuations about those lines that they were swimming in, you can get the diffusion coefficient. So this is magnetotaxis in the bulk fluid, right? All we're doing is just thinking about the only forces acting on this, the only torques acting on this are the magnetic torque and the viscous torque. Once you hit a wall, you also need to think about the solid body interactions. You're covered with 1,500 flagella, so what happens when they bang into a wall? So now let's move from fluid to interacting with a surface, and we'll start off with the simplest surface we can find, which is just a wall. So you'll see this better once the movie starts. This is a consortium. I have a magnetic field pointed straight upwards. And you just say, in the simplest case, the wall does nothing but prevent their forward motion. Then we know what the rotational diffusion coefficient is. We know what the magnetic moment is because we just measured both of those. So the prediction here is that the bacteria would swim into this wall, and then every couple of seconds, rotational diffusion would turn them enough to sort of pop over to the side. So they should sort of stick to the wall and just sort of slide poorly back and forth. Here's what actually happens. So you can see that they aren't even clearly concentrated near the wall. If you squint, you might see that there are a few more over here than there are down here. So they might be concentrating a little bit near the wall, but they're not particularly close to the wall at all. They're sort of vaguely pushed in that direction. If you increase the magnetic field...
Are these within a microchannel?
This is a microfluidic chip. This one, I think, is 125 micron tall. And then this is just one wall on it. Yeah. So all of this is fluid. Everything above this red line is PDMS. So they swim into the wall, and then they sort of accumulate there. So if we look at the video, you can see they are accumulating within this little band. So as you increase the magnetic field, you're sort of compressing them towards the wall. All right. Moving forward. So you do this with a couple of different magnetic fields. At a low magnetic field, you can see ever so slightly decreased concentration. This is a log plot, so you sort of decrease exponentially away. As you increase the magnetic field, you decrease your penetration depth into the fluid. So there's some length scale here that decreases with the magnetic field. And this problem also has a length scale built into it. So gamma is the rate at which you align with the magnetic field. That's balancing the magnetic torque with the viscous torque. So that gives you how long it takes you to align with the magnetic field. And then you've got a swimming speed. So there's a length scale, which is how far do you swim before you align with the magnetic field. So if you non-dimensionalize distance by that, you get an okay collapse. And so it seems that everybody swims a sort of typical distance away from the wall before they turn back to hit it again. If you visualize it, you get trajectories that look like this. So this is one that hit the wall somewhere over here. It got turned quickly, and it turned and it swam away. You can see that it's smoothly orienting back to hit the wall, and then it will hit the wall again and just sort of do that again. So you slowly align with the magnetic field, you hit the wall, you're rapidly turned, and then you slowly turn back to hit it again. I feel like I'm going faster than I was expecting to.
We can
Well,
slow
this
it
is
down.
about 20 minutes. Oh, if you have questions, I'm happy
I have
to
a
take
question.
Cool.
Why would they need to turn once they hit the wall? And why aren't they just stuck?
Yeah, so I actually had some slides about this. So the question of what is actually happening at a wall is neat. So what you can do with this experiment is, I just showed an exponential decay of the concentration. So that's not so far from thinking about an ideal gas under some external gravitational field, sort of exponential decay away from the thing that you're hitting, that you're moving towards. So what we can do experimentally is increase the magnetic field to the point where the distance you swim away from the wall is smaller than the size of an individual consortium. When that happens, this three-dimensional active gas condenses on the surface as a two-dimensional active fluid. And so now everybody's permanently in contact with the surface, and you can track how they move around on the surface. So that's a good way to study just the bacterium-wall interaction. And so it turns out that the rotational diffusion coefficient increases dramatically when you're in contact with the wall, which isn't that surprising. You're covered in 1,000 flagella. You're in contact with the wall. 1,000 proteins are spinning every which way. You get tumbled quickly. So what happens is you swim towards the wall, you tumble quickly, you get pointed in some other direction, and you escape quickly at some random angle. And that works pretty well.
So maybe only tangentially related, but they're spheres,
Yeah.
consortia, and do they have they can just go in any direction, or is it
They go in the direction of their magnetic moment.
just the magnetic moment? That's the key. Thank you. Yes, thank you.
Anything else?
So is there a way to visualize the flagellum in your clusters?
I haven't been able to. They're pretty short flagella, and the only ways that I can figure out how to visualize a flagella are to put some dye on the surface of the flagellum to be able to make them fluorescent. I haven't been able to get any good, you could also do that with dark field. The flagella are really short, and so I haven't been able to see flagella doing that. Maybe a more competent microscopist could. I haven't been able to. And if you do fluorescence, then blue light kills these things instantaneously. And it's dramatic to try to image these things in fluorescence because you take one image and then you take a look and everybody's just dead.
Could you use these like little skipping maneuvers to somehow experimentally measure the attractive potential of the wall?
So it's not the attractive potential of the wall. The fact is you've got a magnetic field pointed in this direction. So this is the distance that you swim before you align with the magnetic field. This scale bar is exactly this distance. So everybody's concentrated sort of within this distance.
Mm-hmm.
If you work out the trajectory, so a few slides ago I showed you the angle associated, how quickly does your angle align with the applied magnetic field. If you go to the two-dimensional trajectory of these, you trace out this U shape, where the width of the U is pi times this distance. Now
Now you have
I'm
plenty of time.
Enough time.
but it lies.
They all do.
Yeah.
So you showed the consortia, they divide.
Yeah, they do.
So are they all of the same characteristic size here?
So you can see it ever so slightly here. This is the outer surface of it. this line here would be separating it from a neighboring cell, but they broke up these consortia a little bit to do this TEM imaging. So you can, if you sort of extend this line down and extend this line down, you get these little pyramidal shapes. So this angle and this length gives you an intrinsic curvature. So what I think is happening is that you grow to the size where the intrinsic curvature makes you start to bend back inwards, and that causes it to divide. That's pure speculation. I think it's informed speculation, but I haven't proven that carefully.
But so in your experiments, they're all of some very close, fairly close size, each consortium.
There's some variability because these are actually from the mud. But yeah.
So when you say they grow, that they're producing more and more cells.
That's right, yeah.
They're producing. And then it gets too large and then they
So you go from sort of, this is probably 20 cells to about 60, being much bigger. Here you can see the edges of those walls clearly. If you look at this on the side, it's elongated in one direction.
Right.
And then it sort of twists and pinches off.
Yeah.
What's the time scale?
Nobody knows.
But you guys observe it. You must have some idea.
We pull them out of the mud. We
Yeah.
watch them for a couple of hours.
Yeah.
And that's all we can see. So you can't watch them over an entire doubling time. There's one person who caught this happening on video.
Yeah.
So you can get some idea of how long it takes to go from this to this, and that's
Okay.
pretty fast.
Okay.
But the entire growth cycle is entirely unknown. I think I punished myself by saying I'm going too slow.
I'm wondering if you increase the magnetic field and look how like these things grow, would that give you any information about the internal magnetic lines?
I don't think so, because the magnetic orientation is entirely passive, right? You can kill the bacteria and they still align with the magnetic field. So what you're doing there is all you're doing is you're changing how much Brownian motion, or active Brownian motion in this case, can misalign the angle between the applied magnetic field and the rest of the fluid. So there's interesting stuff to do when you vary the magnetic field, but I don't know how to turn that into a solid discipline. One thing you can do with that is that people have done is you can carefully measure the magnetic moment of these bacteria and then give it one hell of a big magnetic field. So you force all the magnetic particles to align and then measure the magnetic moment again. And that gives you an idea of how well aligned the magnetic moments are. And the answer is to within a few degrees,
Okay.
which is stunning.
Yeah.
Quick biology question though. In the beginning, you said
Yeah.
that it should help swimming up or down. So like, how do don't they need to also be able to swim against the magnetic field at some point? So how does that work?
The reverse direction. Instead of everybody pushing, everybody pulls. Something like that. You can swim either in the direction of your magnetic moment or against
So
it.
they can reverse.
Yeah.
Okay.
I'll show some pictures where you can
Alright.
see that in a little bit.
And why? And how does it work?
I mean, ask me after I visualize the flow field.
Okay.
I can speculate wildly, but I do have some data, and I'd love to show that instead of just speculating about all these interesting questions. All right, last question.
Yeah, just a quick comment on the curvature
Yeah.
thing that you mentioned. This reminds me of an astrobiology paper that we read, where they studied, they discussed protocells and they modeled them as like these sort of like primitive micelles. And the way that they suggest that these protocells would divide is exactly that mechanism of the curvature taking over.
It wasn't an original idea.
Yeah, these things are just like glorified micelles.
No, they're more interesting than that. All right, so at this point, I just want you to remember that there's this interesting length scale built into it, which is just the distance you swim and the time that it takes you to align with the field. So gamma is the rate at which you align with the field, U0 is your swimming speed, and so you get a length scale out of that. That determines how far away from the wall you swim after you collide with it. So let's move from colliding with a one-dimensional wall to colliding with walls that are all around you. So as soon as you put walls all around you, you now have another length scale, which is how far apart are the walls. So the one interesting dimensionless number that you can make out of this is your turning radius compared to the pore size. If you do the full dimensional analysis, it turns out that there are two other dimensionless numbers that could also be important. One of them is the size of the bacterium compared to the size of the pore. Ecologically, bacteria are very small compared to the pores that they live in, which is just saying the excluded volume of a bacterium does not affect its ability to swim through holes. Fine.
What sizes are over here?
What?
What sizes are over here?
This distance?
Yeah.
Typically 200 micron. My bacteria are 5 micron. They get up to 10. So 1 to 10 is the sort of typical range of sizes for a magnetotactic bacteria. The other dimensionless number would be the rotational diffusion coefficient. That could also matter. So there's another dimensionless number that you can make, which is how much is your orientation decorrelated by collisions with the walls versus how much is your orientation decorrelated by rotational diffusion. And it turns out that you're mostly decorrelated when you hit a wall, just because rotational diffusion isn't that important for these bacteria. So you've got one dimensionless number that's left over, which is how quickly do you align with the field compared to how quickly do you bang into the walls. So there are two ways of writing this. You can either write it as your turning radius compared to the size of the pore, or you could write this as U naught over R. U naught is the speed, R is the size of the pore, so U naught over R is the rate at which you collide with obstructions. And gamma is the rate at which you align with the field. So I'm going to call this the scattering number. So let's think about how this bacterium would move through this complex space if the scattering number is very large or very small. So let's say the scattering number is huge. So the distance you swim before you align with the field is huge compared to the pore space. So there's U-shapes that I showed you before. This U-shape would look like that. And clearly, if you need to swim 10 particle diameters away before you align with the field, you're going to hit the wall a bunch of times before you align with the field. If every time you hit the wall, you get randomly reoriented, then this bacterium would swim up here, hit, get some random kick, and it's just going to bounce around at random within this little gap, and the motion is going to be purely diffusive. So if the scattering number is very, very large, then you cannot move along field lines. Your motion is purely diffusive. That was a very long-winded way of saying that if the magnetic field is 0, then gamma is 0. And if there's no magnetic field, you can't do magnetotaxis. No surprise there. Let's suppose this number is very, very small, so that you swim away and immediately you align with the magnetic field and hit the wall again. So in that case, this bacterium swims away, hits the wall here, rotates, hits the wall here, and it just sort of bounces around in this place. So if the scattering number is minuscule, you swim through the pore space, you hit an obstruction, and then you wait for the obstruction to move. You're going to wait a very long time, and so your average speed through the pore space is very, very slow. So if this number is huge, your drift velocity is 0. If this number is very small, your drift velocity is 0. So presumably, there's some sort of magic number where you can move quickly through the pore space. So the result of the full dimensional analysis is just that your average speed through the pore space compared to your swimming speed is only a function of the scattering number. So now what we want to do is measure what that function is. So we make these microfluidic mazes. All of these little weird star shapes are microfluidic pillars. I can just highlight theirs. And so you get this array of pillars with little pores with narrow connections between them. If I now subtract off the background, you can see this little dot of light here is one magnetotactic consortium. All right, I'm at scattering number almost 4 right now, which means that if you hit this wall, you're going to try to swim to about here before you align with the field. So in this case, the motion should be pretty diffusive. So let's watch that happen. So you can see them sort of banging every which way about. Some of them are moving relatively quickly through the pore space, but an awful lot of them are still trying to find the entrance. The drift velocity through this is pretty slow. I'll show you some numbers in a little bit. But I just want to give you a flavor for this random motion through the pore space.
Pretty good. Look, that one's gotten.
Yeah, I mean, but that's on the sort of front tail of that exponential decay, of that exponential piercing forward.
Yeah.
You got one up there and like 100 back here.
Right.
Your average speed is very small. Now let's go to a pretty small scattering number. So in this case, you hit the wall, you turn back to about here, and then you hit the wall again. So these ones should be sort of plastered to the northern face of each pore. Here's what that looks like. Right? They're sort of stuck to the wall, and now they move quickly through the pore space, but then they get stuck here for a long time. Takes them a while to move forwards.
How do you vary that experimentally?
So the scattering number is U over R. So U is determined. It's about 150 micron per second. R, I can decide what is it based off of how big I make my microfluidic. So I can control R. Turns out it's difficult to vary that too much mostly for dumb reasons, but experiments are constrained by many dumb reasons in this world. So we can't vary R too much, but it's that ratio divided by the rate at which you align with the magnetic field. So if I increase the strength of the magnetic field, you align more quickly.
So it's mostly the size of your magnet.
Mostly I'm varying the magnitude of the magnetic field. So now let's go to a scattering number of 0.3. So now we've got some intermediate value. So now when you jump away from a wall, you jump to about here. If you jump about this far, a typical jump after the wall is just enough to get you through the passageway to the next pore. So in this case, you hit the wall, and you backtrack just enough to find an entrance into the next pore. And here's what that looks like.
That's cool.
Jumping through and just moving admirably past.
Yeah, that's what I would do in a very crowded parking lot.
Exactly.
Back off like 1 car distance and
Yeah.
immediately try a different direction.
I mean, there's very little smart that I'm actually going to say today. But I mean, the whole thing is you should backtrack just enough to be able to get you through the next passageway. Yes?
There seems to be 2 lengths. One is the size of the pore, and the other is the size of the channel.
Yeah.
So,
The opening, yeah.
Yeah, that's right. So both of those matter. In a little bit, we're actually going to solve this numerically, and that'll give you a little bit more insight.
Okay.
In effect, what you end up with is this distance, whatever that is, the distance between the northernmost point and the connections in the channels, sort of determines how much you need to backtrack, and that determines how far backwards you should go. And so that sets what your critical length should be. And the sort of claim is, if you're in any natural place, if you're looking for a hole that leads northwards, you should probably concentrate somewhere in the front half of the pore. So the speed should be so the critical scattering number should be slightly less than 1. If it's more than 1, you're going to go south too much. If it's much less than 1, you're just going to be exploring this tiny region. So the optimal scattering number is always going to be a little bit less than 1.
This is related to that question, but just because I don't know anything about this microfluidic stuff. Is there a reason the pores have this particular shape? Like
Yeah, there is.
A weird shape.
So what this is this is a square lattice, clearly, rotated 45 degrees, so that there's no magnetic field line that will just take you through the entire passageway. Right? Each one of these is a circle. And then with each circle, there is this tiny passageway where there's a direct line through the pore. And so I just put in a little barrier here on the top and the bottom, just so you have to explore the pore a little bit. But basically it's a circle with the shortest connection between the entrance and the exit cut off a little bit.
I had a very related question on the geometry, because like if I would think about sand or like mud, maybe I would be
yes.
thinking about like balls.
Yeah,
and
yeah.
then the highest magnetic field should give the fastest passage.
Yeah, that's right, yes. And
so is that sort of an accepted mud picture?
so what you're talking about right now of saying these entire dynamics that I'm talking about all rely on there being some convexity to the pore. Right?
Maybe, yeah.
Right? So if I built this only with hard spheres, then all of my pores are concave, in which case I can collide with a surface, slide along the surface, and it brings me to the next pore. So why do convexities appear in natural sediment? So if you just have hard spheres, then I agree. Infinite scattering number or zero scattering number is the fastest, but that's not what real mud looks like. So if you have hard spheres and you have biofilm growing between them, those will connect neighboring spheres together and create dead ends that way. The other way that it happens is if you have small particles that got pushed through the fluid, those small cohesive particles can also clog up pores, and both of those make convexities. So the concentration of convexities here is definitely much higher than what I think it is in nature. But I think the convexities are really important, so I made a lattice with a bunch of convexities in. Okay? If it's very quick?
Yeah. In nature, how do bacteria evolve to optimize the scattering number? Is like this speed ideal?
That's sort of what this talk is about.
Okay.
I'll show you at the end. Go. So this is to just give you a slightly deeper flavor of how these bacteria are accumulating within these. So a very high scattering number, you get a uniform distribution. So the color intensity here is giving you the probability that a particular pixel within one of these pores is covered by a magnetotactic bacterium. To move from uniform to sort of, you concentrate close to the exits, versus you swim quickly through the pore and then you get stuck near the northern face for a while before you pop out. And below here are the times that these three particular consortia moved through these particular pores. And you can see that 0.3 does move you through faster than the others. Okay, so now let's actually try to be a little bit serious about this. So what we want to do is understand the relationship between the scattering number and the drift velocity. And at some point, there's a question of, so what we're going to do is we're going to say that there's some rate at which you move northwards. We're going to call that K plus, and some rate at which you move southwards. So for example, this one came in, bounced around, and moved to a southward pore. And so we get K plus and K minus, which just gives you the rate at which you move forwards and the rate at which you move backwards. And you take this lattice, and you go to the continuum limit, then your drift velocity is just determined by the asymmetry in these rates. So if you move forwards more quickly than you move backwards, then on average you drift forwards. So your drift velocity is determined by the difference between these two rates. So now what we want to do is actually measure what these two rates are as a function of the scattering number. So if we only care about the pore scale dynamics, let's go from an entire network to just 3 connected pores. And if I go to 3 connected pores, it's much easier to track the bacteria. And so the bacteria here are these bright dots, and I'm just showing you the tracks behind them. And here's what that experiment actually looks like. So the red one is going to move from here. So that was a transition in the forward direction, and now it's going to move backwards. And so you can see it's sort of moving forward sometimes and backwards sometimes. So if I know how many bacteria are in each chamber, and I know the number of crossings from this side to this side, and the number of crossings from this side to this side, then I can get K plus and K minus quite easily. So I can do that for a bunch of different scattering numbers. Blue here is K plus. So this is smaller than this. So as you increase scattering number, it looks like it goes up a little bit. And then it looks like it goes down a little bit. Red is K minus. So if the scattering number is very small, so you're mostly going in the direction of the field, you almost never go backwards. And then as the scattering number gets to be of order 1, there's some decent chance that you start moving backwards. So, maybe there's a peak there. I think there is. Let me justify that for you. So, I made a big deal at the beginning about how the drift velocity is only a function of the scattering number. So I should be able to simulate this with no fit parameters. So you can just write down, you move in the direction of your magnetic moment. If you non-dimensionalize size by the size of the pore, then your dimensional swimming speed is the scattering number. And you non-dimensionalize time by the rate at which you align with a field. So if I start you off at some particular point, for a given scattering number, I can solve these. There's a nice analytic solution, so you can do your simulations without any discretization of time or anything like that. You have an analytic solution for these blue curves that tell you where you're going to hit. So I just move the bacterium there. When I move the bacterium there, I find the next intersection. I then turn it to some random angle. And so the next time it moves, it moves along this path. So if I simulate this, I can measure the distribution of first passage times, either in the forward direction or in the backwards direction. And so I can get k plus and k minus as a function of the scattering number. All right? So with no fit parameters, that's what the predictions are. And they look okay. I've got more noise in my data than I would like, but life is hard. I'm kind of happy that we got the peak about right. This point right here bothers me a lot. I could tell you a lot about it, but it's not that interesting. It's mostly me. Anyway. So, it does okay. Scattering numbers are pretty, you tend not to go backwards. Then you go backwards more. I systematically overestimate the rate. I think I know why, but, there we have it. And we get the peak and the diminishing pretty well. So this predicts an optimal scattering number of about 0.4. If you subtract k, if you think about k plus minus k minus, that gives you the drift velocity. And this is just the same data rescale, just showing that drift velocity goes to 0 to infinite scattering number. It starts off at 0, and so there's some optimal. So does this have anything to do with reality? So here's my experiment. And the theory matches the experiment reasonably well, and we get a scattering number of 0.4. Based off of what I was telling you before, I'm confident that the optimal scattering number for any realistic geometry should be somewhere between about 0.1 and 1. I can't get, so the shape of the curve that I showed you here, that is a reflection of the specific pore geometry and the width of the channels and things like that I specifically chose. But the sort of general trend of there's a local maximum is generic, and that local maximum is somewhere between here and here is just saying the most likely place to find an exit pointed forwards is somewhere in the northern half of each pore. So the scattering number is the speed divided by the proportionality between torque and angular velocity. So this is just determined by the size and shape of the organism. Here's the magnetic moment. So all of these we can measure pretty well. Here's the pore size. I know what that is in nature because I can go to nature and I can look at the pores. And it's determined by the geomagnetic field, which I can look up on the NOAA website. It's about 50 microtesla. And so the scattering number ends up being, in nature, 0.6, plus or minus 0.2. Yeah, 4 now. Yay! Ha I don't know what I'm going to be doing next year. So, this number is sort of confidently between these two. So at this point, I've got this prediction that says natural selection should tune these parameters such that this number is between 0.1 and 1, And it is. So at this point, we can be confident that that my claim about these things optimally navigating pore spaces is at least not obviously wrong. Maybe I got lucky here. Let's see if I didn't get lucky. So at the start of the talk, I said that bacteria found every possible way of telling the difference between up and down. The sort of absurdity of evolution is that not only did it find every solution, it found every solution many times. So these are 3 different magnetotactic bacteria. I adjusted the size of these images so that these actually show the relative sizes. So this is 60 bacteria all tied together. This is one bacterium that's substantially larger than this. And here's a little tiny corkscrew. So if you pick any 2 of these, they're about as closely related to one another as you are to a mushroom. All right, so these are evolutionarily distinct discoveries. There's actually some debate about whether or not this was actual de novo discovery of Magnetotaxis, or if there was long-range horizontal gene transfer. But at least these are qualitatively different organisms. So the prediction is that as you go from this to this, your size has increased dramatically. So your hydrodynamic rotational mobility has also increased dramatically. So if I look at the variability between these different organisms, the swimming speed changes, the size changes, and the magnetic moment changes. And the prediction is that as all of these things change, this number should remain between about 0.1 and 1. So I just moved everything up here. And now I want to impress you that I know how to use Google Scholar. Because here are a bunch of different values for 15 different organisms. This one right here is the one that I've been talking about this whole time. This particular row, these are my measurements. All the other ones are other people's measurements. I give the citations in eLife. I'm sorry I didn't put their names here. That was careless of me. This is clearly too much information. I only want to convince you that there's a lot of data available about these. If I just delete all but the largest and the smallest from each one of these, you can see that as you move from Brazil to Germany, the magnitude of Earth's magnetic field doubles. The swimming speeds increase by an order of magnitude. The magnetic moments vary by 2 orders of magnitude, and the mobilities vary by 3 orders of magnitude. So this is substantial variability. So now if we're going to take 4 numbers that all vary tremendously, or some of them vary tremendously, some of them vary considerably, and I multiply them together, if what I'm saying here is wrong, I should end up with scattering numbers that are just all over the place. So this pink line shows you random phenotypes. So all I'm doing is just bootstrapping the phenotypic diversity of magnetotactic bacteria to get a sort of range of what the scattering numbers would be if all these variables were uncorrelated with one another. And this little point here is my particular bacterium that I've been talking about. So this is right at 0.6, just as I showed you. So now if we look at the other ones, they're sort of within that band of 0.1 to 1. And so it does seem that natural selection is creating correlations between these different parameters to keep them squished within this narrow region of parameter space where things can efficiently move through the pore space.
Sorry, did you use the same R Pore for all of these?
I did, yes. So I did that mostly because people who study magnetotactic bacteria don't report the pore sizes that they're living in because they didn't think it, because they take bacteria out and they look at them. So this is the pore size. So the error bars here are just reflecting my best guess of uncertainty in pore size. And so all of these correspond to medium to coarse sand, much like you would find on any beach or in shallow rivers or things like that. So I'm actually pretty confident about my choice of R Pore, but I would love to have an excuse to fly around the world measuring grain sizes. All right, so let's finish this up. So to a pretty good approximation, all the bacteria within here are equally and optimally efficient navigators of the pore space. They're all close to that maximum that we understood a little bit from physical reasoning and the simulations and the experiments. Let's move on. So, what does this teach us about anything? So, some of you who study biological fitness could have come into contact with the word fitness landscape, which is just saying fitness is some scalar quantity. It's basically how many babies you have. The more babies you have, the more fit you are. So that is some function of your genotype. And so you can imagine writing a scalar function of your genotype that tells you how fit you are. And so what we're seeing here is a one-dimensional slice of that fitness landscape. And it's smooth, and there's a single global maximum. So there's this idea here of, evolution moving you towards global maximum. And I think that this is a reasonable way of showing what that landscape looks like. At least one low-dimensional slice of that landscape. There's also this sense in evolution of when we say that something evolves to be fit, we're somehow saying that its phenotype is a reflection of its environment. And I think it's easy to have sort of loose intuition for that, about, things that live in dark places have big eyes and things like that. But what we've got here is something that's at least dimensionally correct. So on the left, we have the swimming speed, something that's basically the size and shape, and the magnetic moment. So natural selection can act on all of these. Over here we have the pore size, which is just sand grains, the geomagnetic field, and the critical scattering number is just something about the shape of the pores that are in your environment. So you get an equation here that's relating the things that natural selection can act upon to the environment that's dimensionally correct. And I sort of like that as a foothold to understand evolution. The other sort of thing that I like about this result, it makes me happy, I'll admit it, is we think about natural selection as optimizing life, right? There's always the story that people tell about the giraffe having its very long neck to reach the topmost leaves. And that's sort of unsatisfying. And actual clear examples of optimality in nature are pretty rare, because optimality is this one tiny point. And the fitness landscape is very high dimensional. So how do you find a low dimensional point in a high dimensional space? It's easy to wander forever without actually finding that optimality. This optimal solution is highly degenerate. I was able to vary rotational hydraulic mobility by a factor of 1,000 and end up with organisms that are equally efficient. So this degeneracy, what I'm saying here is that optimum isn't a point, it's a two-dimensional sheet. And it's presumably easier to find that two-dimensional sheet than a single point. Also, the other problem with optimality is that it's very fragile. Right? If my hand is optimal for writing with a pen, if I get into a fight, my hand is going to shatter. Right? Every phenotype that we have is adjusted to do many different tasks. And so what this degeneracy is doing is saying, you can be optimally efficient while at the same time balancing, you can, while tuning any two of these three parameters to the local situation that you live in. So the robustness of this optimality is a result of its degeneracy. So with that, thank you.
So you also mentioned that bacteria basically use every mechanism they can find or that exists to navigate. So are there other compatible observations of, say, bacteria that navigate with Earth's gravitational field or light fields or things like that?
So I've got a scattering number here, which is decorrelations by collisions with the environment compared to decorrelations with coupling to your compared to aligning with whatever field you're coupling to.
Yeah.
I think the scattering number is probably general across a bunch of different organisms.
But have people done the experiment where I guess gamma now they would have to tune a light field or tune?
No, but if you're on my next grant committee, I hope you'll remember that's a good idea.
Like a big,
Oh yeah, right. Yeah. So I've got ideas for how you can do this with phototaxis.
Right.
It's very hard to carefully shape chemical gradients over this scale and know what they are. So I think chemicals are hard. As you just point out, changing gravity is also tricky. So I'm most optimistic about trying to generalize these results to phototactic bacteria. But that's on a long list of interesting questions you brought up today that I haven't made any progress on.
Very inspiring. What question?
So, the source of your uncertainty bars is from a limited amount of tracking? You know, in your scattering plot. No. Yep.
This one?
Yep. So, is it you have a population of these organisms and they die, they reproduce?
No, it's nothing so elegant as that.
How many tracks you take?
It's how many tracks you take, basically. So you've got limited time to make these measurements before their swimming speeds start to change as they die. So these have to be very quick experiments. And then you also need to load up enough, you need to get enough consortia within the pore so that you can get a lot of tracks. But you also can't have so many that they start to pile up here.
Yeah.
So that there's sort of a narrow range where, I mean, it's difficult to get as many tracks as I want, and that's sort of short of it. The other thing that happens is, if I play the video again, you'll notice that right here, there's a bacterium that's swimming around in circles because it hit the wall. When that happens right here, it looks like a bacterium is swimming in and out of the pore very quickly. And so you get very high rates there. So having an experiment where you can do decent tracking so that the transition rates actually correspond to reality and not, bacteria getting stuck in the entrances is also something that's limiting.
So how many tracks do you need for each of these points?
So each one of theirs is something like 100.
Oh, that's
tracks, 100 consortia that pass back and forth through this many times. And that's sort of, that's sort of the limit. It's about 100. I think the error bars would be smaller if I could get 1,000, but that's sort of the limit.
So your lattice of pores is very regular.
Yeah.
What would happen if you introduce randomness into that?
Yeah, so I think not much. So the reason I like the regular lattice of pores is that if I did an irregular lattice, then in order to get this curve, my error bar, I would have to do this experiment enough times so that I could average over the heterogeneity. Right? So instead of each one of these pores, so each one of these dots corresponds to about 10 hours of experimental time for building the device, loading it, putting the bacteria in it, discovering that you had a leak, starting over, doing it again, getting the tracking going. So if I had an irregular lattice, then there's no way I could get even this much data. Well, what this much data does give me is it lets me make sure that each one of these bacteria have collided with the walls in enough places that their statistics are corresponding to these first passage problems that I was doing in the simulations. So the fact that I can get this with no fit parameters tells me that this is a pretty good model. And this is a pretty good model, which means that I can now just throw it into a computer in an irregular lattice and watch how it comes out. So I think that what I did is I figured out what field equations I need to solve, and now I just need to change the boundary conditions considerably to move towards reality. But, that's also true. Ask me in a year. I've got a student working on exactly that right now.
Good.
Is there a way to track, like, sort of distinguish the dead bacteria versus the ones which are not?
The dead bacteria aren't moving, which makes it easier.
But they should still react to the magnetic field.
They rotate to the magnetic field, but they don't swim.
Mm-hmm.
This is a flagella. That's what swims.
Right. Okay, well, in the interest of time, I think we'll turn the rest of the conversation
Thank you.
offline. Thank you so much.